Okay, hello. In this video, we're going to look at recursion. So we're here, and there's a few examples that we have prepared. We're going to try out doing some pictures in here, see how that goes. All right. We'll also keep some notes over here in the core information. So the basic idea to remember about recursion is we're going to be inside of a function and we're going to call itself. And so you could potentially think that there would be an issue with how is that going to be organized and what does it mean. All right, so we will look at some code and draw a picture. Right, we're going to start with, okay, so this is in the usual place, in my directory in the class, directory called recursion. Okay, so here we have a program hello.c. First, just going to run it. Okay, now we see it run, it prints 3 times hello. As any C program, we come into main here. There's say hello with 3. We put a 5 here. Let's see how it would change. It prints 5 times. Okay, so I'll put that back to 3. And we can see what happens here. But first, before we look at that, I want you to look here. So most of you are used to doing programming with loops. This would be your loop to just do something 3 times. You have a variable, you start at 0, you go up to 3, you increase by 1, and then in the loop you do something. So in terms of the doing something with a loop, you have a couple different parts here. This is the do something, and then for a for loop, start at 0, go while less than n, and up by 1. So those are the basic steps of your for loop. With recursion, there are going to be 3 basic steps to any recursive program, any recursive function. There's going to be a base case where we stop. That's kind of like this condition here. So we always have a place where we're going to stop for a for loop. And recursion will have some where we stop. There's going to be something that we do. And then the difference is with a loop, what we have is we're always doing this I++, and then the language will go back to the beginning. So the language will say that after you do this here, we go back to the beginning of the loop. That's part of the definition of the for loop in the language. With recursion, we're in charge of starting things over again, and we do that like this. Okay, so to show what's happening here, maybe I'll go back to, okay, we'll go back to 3, and we're going to draw over here a call tree. So what a call tree is just going to be a picture of where we are inside the program as we run. So we're going to run the program, and I'm just going to have which function we're inside of. And we start off, we're inside of main. I'll put it like that, and then inside of main we have some variables. argc is something, argv is something. Go ahead and make that look like a box. Alright, so that's where we are when we start the program, and when we say hello 3, then we're going to go into the say hello function. So I'll put that here with say hello, and there's a 3 being passed in there. Now we need to go and look at, that goes into a variable called n. So inside of say hello we have n, which is 3. That's the only variable inside of say hello. And I'll draw a line in between these to represent that we went from main into this say hello. And let's see, we'll put over here the screen. So at the beginning, there's nothing on the screen. Okay, we start off, we say we're inside of here. N is 3, so we skip past this if and we print hello and a new line. So hello and a new line, there it is. And then we call say hello again. So the key thing to understand here is that we're going to start a complete new copy of the function. So this one's still there. Now we're going to have a new copy of the function that's going to run. And inside of there, remember we're right here, we're about to start a new say hello. We do n minus 1. N here is 3, n minus 1 is 2, so when we create this new version of say hello, it has n equals 2. And we'll draw the arrow to show that we went from this one to this one. Okay? Alright, so now we're inside of this one. Say hello. We are do the if test, we check. We don't do that. We do the printf. So over here we do a printf hello and a new line, and then we call say hello again. Remember, we're right here on this one. We're going to start a new copy of say hello. And now we're going from this one. There we have n equals 2. And we do n minus 1, passing into the new copy of say hello, so that's a 1. Alright, so now we start this function. It's all set up, we're ready to start it. Check the if test. We don't do the return. We do the print of the hello. And then we do say hello again. And we're going from this one here, so we have n equals 1, we're doing n minus 1, so we go into say hello with a 0. Okay, we have everything set up in here with this version, this copy of say hello to run. We do the if test, n is equal to 0, so this is a true here, and we return. That means that this is done. And maybe we will, I don't know, we'll put a background color on to say that that's done. So that returns back through its arrow. So who was waiting was say hello, the next copy up had called us. And that means that the say hello with n equal to 1, it just finished this part of its code right there, and there's nothing after it, so then this one would be done as well. And we would color that off to say that that one's done. And this one, where did it come from? It came along this arrow. There was a say hello with n equal 2 that had just finished calling its child. We could call these children. So then this one would be done. And it just goes up the line until we're at the say hello with n equals 3, that's where we started, and its child that it called is done. And then the control would pass back to main. Whenever a function's done, it goes to whoever called it, and then there would be, main would be done, and that would be the end of the program. Okay, so this is a call tree. It doesn't look like a tree, but it does look like we can trace through and see the order that functions were run. So one thing that we could say here, call tree is a picture of functions that called each other, what was running. Okay, so we'll do another one of these. And we should check back the three main parts to a recursive function here is you have a function that calls itself. There's got to be some base case somewhere that you stop calling yourself. There's something that you do that is the main action, and then you call yourself with some different parameters than what you started with. So those are three parts to any recursive function. So I'll put here three parts to any recursive function. So base case, where you stop calling yourself, to do something, and three, recursive call with different parameters than you started with. And the reason the parameters should be different than what you started with is that way you will be making progress towards getting closer to the base case. Let's take a look at another one of these that we have prepared here. Sum n. So we'll look at sum n.c. Let's go ahead and run this program. Okay, so sum n. If I run s, it prints 55. And what this function here, addin, is supposed to be doing is returning 1 plus 2 plus 3 and so on up to 10. And 55 is the right value. So if we look at it here, this is a recursive function that actually returns a value. Why don't we go with calling this with 3 so that we can draw the tree to see how we would draw this, and the value there is 3. So let's go over here in a new slide. We'll get rid of these. Okay, so now we would be inside of main, and we're going to go and call, let's see, there's a variable called total now inside of main. And when we get to that part of main, we have total. We're going to call addn. So we need to have an addn function. So in here, we'll do addn. Inside of addn, we have a value n, which starts off being 3, because this 3 gets copied into that parameter right there. Okay, so that's what we have. And we also want to keep track that whatever that returns is going to go into total. So we need to draw a connection there, and I'll draw the connection like this. Okay. We can also keep track that main called this addin here. That's where we are. We're ready to start addin. So inside of addin, what do? We do an if test. That's not true, so we don't do it. Now we're ready to return n plus, we have to do a recursive call. So let's see what the recursive call sets up to be, and then we can see how we might draw what's going on here. In the recursive call, we're doing n minus 1. That's 2. Now whatever that is, we're adding, this function here is doing 3 plus whatever this thing returns. So now I'm going to draw a squiggle. So whatever this returns is going to go into the return value for that guy. That should have been a squiggle. Let's see. So whatever this one is returning is going that. Okay, we'll do it like this. All right, we'll leave it like that for now. So whatever this one's returning, it's going to be 3 plus 3 plus this. So this return value here is 3 plus. We can drag this over so it kind of looks right. So whatever this returns, it's going back, and 3 plus that is going to go back up to the total. Okay. And now we're inside of this addn with 2. That's ready to run. And if we look at where it came from, so addn with 2, that's going to go and say the if test, it's not less than 0, so it goes ahead and it's going to do the same equation. Now this is going to be 2 plus addn with n minus 1 is now 1. So there's a recursive call, there's another copy there, and then whatever this returns, here is going to go together with 2 plus that. So we're going to have 2 plus whatever this is. We'll go back up this way, and then that will get added up with 3 to go back to the total. Now these are all still, so just a pause here, where we're at is we started in main called addn called itself, it called itself again, and that's where we're sitting. We're still in the middle of running these addns. These are all kind of open. These are all kind of open in the system right now. And we're at the point of starting to run this one. So now if we go into this one, we do the if check, n is greater than 0 still, so we're going to do this formula again, which has another recursive call. So we have this recursive call, and that's coming from this version of addn there, where n is 1. We're calling it with n minus 1. That means this will be 0. And whatever that returns is going to go into this value right here with a 1 plus that. And then we're ready to run this one right here. So the addn with an n value of 1 here, it does return 1 plus the recursive call. And then we have this recursive call right here is n equals 0. So we finally got into our base case. When we get to n equals 0, it simply returns 0. And we could put that here by saying there's a 0 going back. So we could draw that 0 here. So this 0 is going back, and that goes back to the addn. Let's see, and we could highlight this. We can highlight this to show that it's done now. The value of 0 is sitting here, and it's in this 1 plus 0 formula, and that 1 plus 0 was sitting as the return value for addn. This addn here, So now we're going to have, and why don't we make this smaller? Okay. So this 0 is a return value from that box that's highlighted. That gets added on to 1. So that's going to be a 1 coming back on this arrow. That's a 1, and that's the return value from this copy of addin. So we'll highlight that one. Now there's a 1 sitting there. Where did that come from? It goes into the formula for the return value for this copy of addin. 2 plus 1 is 3. So that will be the return value coming out of this addin. And that will be the return value, and that means that this one is done. So now we have a 3 sitting as the return value for this copy of addin, and that went back into the formula for the return value for this one, which came when we were in addin here with n equal 3. So we have that 3 plus 3. Now that's going to be the return value that's going back from this copy of addin. Which goes back to main. This copy of addin would be done, and inside of main we'd have total is 6, and then that is ready to print to the screen. Alright, so this is a recursion tree, a call tree, where we see values being passed back with return values. Okay, we'll look at one more example here and then be done, because it's getting to be about the maximum amount of time you can handle. Let's look at exp(n). So let's do print power 2. So I'm going to run this. And we see a bunch of dashes printed. If I change that to be 3 instead, I see fewer dashes. If I change it to be 2 instead, there's fewer dashes. And what this is doing is it's taking this value here and doing 2 raised to that power. 2 to the second power would be 2 times 2, which is 4, and that's how many dashes it prints. If I had a 4 there, it would be 2 times 2 times 2, which is 16. And that's what we started with here. Okay, that's what it's doing. Now I just want to draw what the call tree looks like. Or perhaps, so we'll look at let's look at the code first and then draw the call tree. Okay, so in the function here, it's a recursive function. There's a base case, there's something that we do, and there's recursive calls. So here's 2 base cases. If we get something less than 0, I don't want to deal with negative, what that means, 2 to the negative power. I don't want to draw all dashes for that, so that just returns. If n is equal to 0, so 2 to the 0th power in math is defined to be 1, so I just print 1 dash. Okay, then we have our recursive calls here. Ignore this, it's not important for what we're doing. These are 2 recursive calls, so now instead of calling it just once, I have it called twice. Okay, so if I have 2, suppose that if n is 4, Okay, so then what I do is I call print power 2, and this would be a 3, and print power 2, 3. Okay, so why do I do that twice? So if n is 4, how many things am I supposed to draw? 2 to the 4th power is, so it should draw 16 of the dash character. That's what I'm claiming this is supposed to do. All right, what would this do? So print power 2, if it's correct, then this should print, sorry, this should be 16. So this should print 2 to the 3rd power, which is 8. And this should print 8. Okay? Because I'm trying to do powers of 2, if I do 2 copies of these, that should add up to the right thing. Okay, so this is another key property of recursive functions, that you're relying on the fact that you've done the correct thing. So I'm relying on the fact that I can do print power 2 with 3, and if that's correct, then I know I'll get the right answer for n equals 4 as well, because I have 2 copies there. So that's a key thing in understanding. So we'll put this as a key idea. You assume that your function is correct for smaller values of n, and use that to get the right answer for current value of n. And this is very similar to induction. And that's not a coincidence, they're basically the same thing. Okay, but so this is the code that we have. I'm going to ignore this part right here, pretend it isn't there. It just makes the formatting nice to have a space in the middle. But for drawing the recursion tree, the call tree, it doesn't matter. Okay, so let's draw the call tree if I have 3 here. So it's going to print 2 times 2 times 2, 8 dashes. So I'm going to do another slide here. And we always start in main in C. There's no local variables there to speak of, and we go straight into the, so this is, we don't have a total here anymore. Now we're going to be in print power 2 with a 3. So I'm going to put this over here. We need a little bit more space in the end for this one. So print power 2 with n is 3. N is my variable there. I went in with a 3, and I'm going to squeeze this in. There's no return values here. It's only doing printing, so I don't have to worry about those arrows. All right, so when I'm in print power 2 with n equals 3, go ahead and draw this line here to show how we got there. So what does it do? It checks these values, and then it's going to call print power 2 with n minus 1. That would be 2, but it does it twice. So we draw that with two copies, because it is 2 different copies. It does it 2 different times. It's not the same. It does the same thing, but it does it twice. And we draw a line to say this is how we got there. Okay, so to figure out what this does, we have to do it twice, and so now we have 2 different things that we have to go and look at. We have to look at this one and we have to look at this one, and they will do the same thing. So let's look at this one first. So it comes in with an n value of 2. It checks the f-test. Neither one of those is going to happen. So it's going to do these two things. So again, it's going to make 2 recursive calls. And now the value of n goes down. We'll have n equals 1 on both of those. And the same thing will happen for this one. That when we do this one with n equals 2, we're going to get 2 copies. To figure out what happens with this one. Okay, let's look at this one here, n equals 1. What happens there? We come inside, we don't do either one of these, we do 2 copies of print power 2, and now it's going to be with a 0. And we're starting to run out of space on our screen here, so see how much of this we can fit in. So both of these are going to be a 0. Those both came from this one here. Okay, I think I will not draw the rest of these. So what happens when we get into this one? We are at n equals 0, so it will print a dash. If we had a picture of our screen over here, then when we do this one, we would have a dash. And then it would finish. And when this one finishes, I guess we can go ahead and put the screen over here. So we'd have a dash. When this one finishes here, it goes back to its parent, whoever called it, and whoever called it was with n equals 1, and so this line here just finished, and then it goes and does the next one, which prints another dash. And so then that one would be done. And this print power 2 with n equals 1, even if we were looking at this line, that doesn't happen, and then this one would be done. And it goes back up to its parent. And so it was called by a print power 2 with n equals 2, and what happens next? So this was a print power 2 with n equals 2, it just finished the first recursive call, it goes into the next recursive call, and then that would go down one more level with 2 children, just like this one. And so now we can use the key idea here that you assume the function is correct for smaller values of n. So we know now, because we did this part here, that print power 2 with n equals 1 prints 2 dashes. So we could just take that for the rest of these. It's going to print 2 dashes. This one prints 2 dashes, and then it would be done. It prints 2 dashes by doing 2 recursive calls, and then this one here would be done. And so what has this done? With n equals 2, it has printed 4 dashes. We go back, so where did this come from when this one finishes? It came from print power 2 with n equals 3. So that was the first recursive call in the n equals 3 copy. It printed 4 dashes, and then it calls the same function again, and we could use that we know that's going to be 4 dashes. The way it does it is doing all these recursive calls, but now we would know that there's going to be 8 dashes. And an extra space if we're looking at this if test. Okay, so you might want to take a little pause and Just look at the code, look at the picture. All right, so some terminology here. These are called call trees. This one here looks more like a tree, maybe an upside down tree because it gets bigger towards the bottom, unless you're looking at the roots of the tree. So this could be the roots of a tree. This is also called a recursion tree. And some other terminology that we can put in here. So we can look at the depth of a recursion tree. So I'll put a column here to say there's depth. So depth is just how far are you from where you started. And you either start counting at 1 or 0. I'll start counting at 0. Okay, so this is at depth 0 right here, that part of the picture. And this here is at depth 1. And we're going to have to move these over. Now down at the next level, we're at depth 2. And at the bottom, we'd be at depth 3. Okay, so if we ask about the depth of recursion or the depth of our tree, then it just goes like that. We can also ask about how many boxes are there. We call these boxes nodes. Just because. So let's get rid of this screen, and then we'll have room. So the screen goes over there. How many nodes or how many copies of the recursion do we have? Okay, so I'm going to add these up per level. So I'm going to just take all of these. Let's see, no. We'll take these. Those will give us our boxes. So how many nodes do we have at this level? There's 1. How many nodes do we have at this level? There are 2. How many do we have at this level? There are 4. How many would we have at this level if we drew them all? Each of these has 2 children, and there are 4 of those. So there are 8. If we were in general doing this higher, and we were at some level, say K, further down, we just kept doing the same thing, and we had, instead of starting at n equals 3, we started at n equal k. How many nodes would there be? And the answer is 2 to the kth power, and okay, so that is the general formula. Because we had 2 recursive calls at each level, then we have 2 to the k many nodes. All right, so your key ideas for recursion: a function calls itself. There's always going to be 3 parts. You have a base case where you stop, you do something. So here we did something at the base case. Then you make recursive calls with different parameters that gets you closer to the base case. We saw a few examples here. And there are, let's see, there's a few others that you can look at in here that have some comments about what they do. Some more general comments about recursion. Anything that you can do with loops, you can do with recursion. So anything that can be done with loops, put that in bold, can be done with recursion, and vice versa. They're really equivalent. It's just a way of repeating things. And we do have multiple copies of the same function running independently. So they're all running in their own boxes with their own sets of variables, and they're connected by whatever the program, however it's written. All right, that is definitely plenty for this. Have fun with recursion.